Welcome, ladies and gentlemen, to the Mechanical Properties lecture for thermoplastic resins. So we're going to go all the way back to the basics, which is stress and strain. And when it comes to stress and strain, we are looking at a wide variety of properties or parameters that we're trying to get from a mechanical sample. The one you hear most often is tensile strength, and this is how much stress a material will endure before permanent deformation. You also will hear about compression strength, flexural strength, elongation, stress versus elongation, which creates the stress-strain curve, and the modulus. And a modulus is how a material resists deformation, or the rate of change of the stress to strain graph, or the slope of the initial strain. There are different types of moduli, which I will talk about briefly. So, the basics. Stress versus strain, or load deformation. Stress, as it is defined, is the ratio of an applied load to the original cross-sectional area. So stress is often denoted by the sigma, is force divided by area. Strain is the change in length per unit of original length. So it is, I believe this is eta equals L minus L0 divided by L0. So those are the equations for stress and strain. No, I'm not going to be asking you to give me equations, but I do want you to know the definition of stress and strain. This is a schematic of tensile testing. You have a clamp here, you have a clamp here, and you put your sample in between these two with the grips. And then these clamps pull in both directions to develop a stress-strain curve. We call it a stress-strain curve. What it really is a load versus elongation curve. And quite often you will have something called dog bone sample. It's bigger on the ends and a little more narrow in the middle where the gauge length is, or you'll just have a strip. But this is a traditional tensile testing setup. This is some examples of what you would see as your output from tensile testing. Stress is here, strain is here, and you will get curves that look like this depending on what you have. Now if you have a really brittle material, you will get this sort of straight line and then brittle failure, just breaks. If you have a really ductile material like an elastomer, you'll get this kind of very shallow but long drawn out curve where you get ductile failure at the end. If you have a typical plastic, you will get an elastic region, a yield point, you'll get your plastic region, and then you'll actually get your failure. So this is a ceramic or a brittle plastic, a traditional plastic, and then an elastomer that are conveniently color-coded for your reference. This is a typical stress-strain curve for a plastic material. Now you might be able to pick up from this slide that I want to emphasize the area under the curve. The area under the curve is the parameter of toughness of a particular material. And toughness is not some sort of abstract concept. It is an actual quantifiable amount, and it is the area under the curve. There's wide varieties of regions where you can get different information from a stress-strain curve, and I'm going to point a few of those out. So this first region is the elastic region from this point to this point. Basically it's from the beginning of testing to the yield point. After this yield point, that's where you get permanent deformation in the material. Before this point, any of the deformation will recover elastically like a spring, and that's why you get this called the elastic region. After the yield point and right before the point of rupture, you get ultimate strength. That's the point right before it fails. So after the yield point, but before the point of rupture, you have the plastic region. You'll get elongation, but a lot of this is permanent deformation. It's not going to spring back to its dimensions that it had before. So your yield elongation is the point right before it starts to permanently deform. Your ultimate elongation is the point of elongation at the point of ultimate strength. Ultimate strength is essentially the data point immediately before the point of rupture. So you can do one test with one sample and get a whole lot of information, and that's why tensile testing is really valuable testing. So this is a list of terms and definitions. The one I kind of went over a few of these before. The only one I didn't talk about was modulus of elasticity, and that is the ratio of stress to strain within the elastic region of the stress-strain curve. Well, what the heck does that mean in actual real-life terms? What it is the slope of this line. So it is the initial slope of this line is the elastic modulus. So if you're going to talk about elastic modulus, that's what you're actually talking about, is the slope of this region, of the linear region of this line. The rest of them I kind of already went over. So you'll probably see this stress strain curve on an exam, so it's in your best interest to understand this. So we have 3 different materials here. This red one up here has high strength, low ductility, and low toughness. Why does it have low toughness? Because the area under this curve isn't all that big. Low ductility because its elongation is rather short, but high strength because it can withstand a lot of stress. Now this green one, it has low strength because where it fails is relatively low on the stress curve, high ductility because it has a really big elongation, but low toughness because again, this area is not very big under this curve. It's the middle one that we characterize as a tough material. Relatively high strength because it gets pretty high on the stress curve, relatively good ductility because it gets pretty far on the strain axis, and high toughness because the area under this curve is large. So once again, these are color-coded for your convenience. Red is brittle, blue is a tough material, and green is an elastic material. So this is a stress strain curve for an amorphous plastic. Once again, we see a really typical stress strain curve. We have our elastic region, our plastic region, and then our brittle fracture region. What is actually happening within this plastic in terms of the molecules is you have things that look like a bowl of cooked spaghetti. Then as you start to pull on the ends of the sample, you physically start to align those molecules. And the more you pull and the more you pull, you can actually align those molecules until you pull them to the point where you break them, like you would snap a rubber band if you pulled on it too hard. So that's what actually is physically going on with the molecules in a sample. When it comes to a semi-crystalline plastic, other stuff is going on. In an amorphous plastic, we don't have any crystallites, but they are present in a semi-crystalline plastic. Now the stress strain curve looks very similar, but how the plastic actually deforms when you apply a stress to it is different. So at stage 1, this is before deformation, this is right before you load it into the clamps. And then at stage 2, you start to get an elongation of the amorphous phase. So you have these amorphous phases in between, and you actually start to line those up. Then you actually, those are all fully aligned in stage 3, but then you start to actually kind of tilt these lamellar chains, and then you start to align those as well. You can actually kind of fragment these apart, and that's where you get the separation of crystalline block segments in stage 4. At stage 5, you get orientation of these block segments, and then these amorphous tie chains are all the way stretched out, and you pull on this a little bit more, and you're actually going to start to snap these amorphous tie chains. So you're going to get a curve that looks very similar, but what's actually happening to the molecules is a little bit different in an amorphous versus a semi-crystalline plastic. You can induce crystallization by force if you have something that's in the amorphous state, but then but it has the ability to crystallize. Again, we have a really high quality graphic here, so please please don't hold that against me. But what you start to do is you have all of these kind of amorphous chains that are jumbled up, you start applying force, you start to get necking, and then if it has the ability to crystallize, you will get an orientation of those, and they can actually crystallize within the sample prior to rupture. So here are some stress strain curves for some typical thermoplastics. We have polymethyl methacrylate, which tends to be kind of brittle. It doesn't have really good elongation, but it does have really good tensile strength. ABS has a similar issue. Here we have nylon 6 or polyamide 6, and this has really good tensile strength and very good toughness. When we start to look at things like polypropylene or polyethylene, we start to see a lot more ductility and kind of moderate strength. And then when you look at LDPE, you have something that looks kind of like an elastomer in terms of its properties. So this is just some typical stress strain curves of typical thermoplastics. So to summarize, mechanical properties are by and large determined from a stress strain curve. There are some other things like compression or impact strength that we use other types of testing for, but your typical tensile test can give you a lot of mechanical properties information, like the yield, the ultimate elongation, as well as modulus of elasticity, and then percent elongation from one test. So if you know how to read a stress strain curve, you can get a lot of information about the mechanical properties. This is the end of the mechanical properties lecture. This will be part of a larger quiz, so please move on to the next videos, and I will see you there. Bye.